Welcome to today's episode, where we're diving into the intricate world of distributed systems and the crucial role that robust communication protocols play within them. As technology evolves, it's essential to grasp how different components of the system interact with one another. A failure in one area can create a ripple effect throughout the entire architecture, making it more important than ever for developers to understand these dynamics. So, let's explore some key concepts that help in crafting resilient systems capable of tackling various challenges. At the core of distributed systems, we find multiple interconnected components that communicate and coordinate to achieve a shared goal. This interconnectedness, while powerful, introduces a layer of complexity, especially when it comes to communication. If one part of the system fails, it can lead to cascading issues that impact other components, potentially resulting in system-wide problems. To counter these risks, developers need to implement effective communication protocols. This includes strategies like circuit breakers, validation processes, and retry mechanisms. By anticipating potential failure scenarios, developers can design systems that not only function well, but also recover gracefully from failures. Now let's talk about one foundational concept, fair loss links. So what are fair loss links? These are communication pathways that allow messages to be sent without guaranteeing their delivery. While this might sound risky, it can actually reduce the overhead associated with ensuring that every single message is received. However, it does bring its own challenges, particularly around message loss and duplicates. To enhance clarity in communication, acknowledgements come into play. They serve as a signal to the sender that a message has been received. Yet even with this mechanism, issues like message loss and duplicates can still arise. This is where idempotent operations become crucial. Idempotent actions can be repeated without causing adverse effects, which means that even if a message is processed multiple times, the outcome remains consistent. Another vital aspect of distributed systems is managing the order of messages and effectively handling duplicates. This is where sequence numbers are incredibly useful. By assigning a unique sequence number to each message, systems can keep track of the order in which messages are sent and received. This helps with deduplication, ensuring that each message is processed only once, even if it arrives multiple times. Despite these strategies, achieving what we call exactly once delivery remains a significant challenge in distributed systems. While this ideal is tough to reach, developers can turn to alternative strategies like at least once and at most once delivery methods to boost reliability. Understanding these delivery semantics is essential for building effective communication protocols. Now, let's zoom in on the at most once delivery method. In this scenario, the sender transmits a message without expecting a confirmation of receipt. This can be an efficient approach, but it carries the risk of message loss. If a connection is interrupted before the acknowledgement comes through, the sender might not realize that the message never made it. To tackle these challenges, we can look at the Transmission Control Protocol, or TCP for short. TCP breaks messages into packets for transmission, incorporating mechanisms for retransmitting packets to ensure they reach their destination. It also uses sequence numbers to manage the order of packets, helping to prevent duplicates by identifying and discarding packets that have already been processed. However, even with TCP's robust features, connection interruptions can still lead to scenarios where messages are resent, resulting in potential duplicates. This underscores the importance of designing systems that can gracefully handle such situations. For many developers, the ultimate goal is achieving exactly once processing, where duplicate deliveries don't produce undesirable side effects. For this to work effectively, all nodes involved in the communication need to have a shared understanding of the message's state, specifically whether it has been successfully persisted or not. While reaching this level of consensus can be theoretically challenging, practical approaches often involve relaxing coordination requirements. This way, developers can ensure reliable message processing while still keeping the system efficient. As we wrap up, it's clear that the complexities of distributed systems demand a deep understanding of communication protocols and the challenges they present. By exploring concepts like fair loss links, acknowledgements, idempotent operations, and delivery semantics, developers can build systems that are not only functional, but also resilient to failures. While the quest for exactly once delivery is ambitious, employing strategies like at least once and at most once delivery can significantly enhance the reliability of distributed systems. As technology continues to advance, mastering these principles will be essential for creating effective and fault-tolerant systems. Thank you for joining us on this journey through the world of distributed systems, and we look forward to diving deeper into these topics in future episodes.